Yeah.
Hi, everybody. It's another Wednesday. I don't know how that happened, but here we are. So we're going to be doing another Wednesdays with Wendy. And today we're going to be talking about GPS and how GPS can help us understand the motion of the ground. So I've made these little GPS instruments out of craisins and toothpicks, and we're going to be using these to stand for real GPS instruments. Clearly, these aren't real. So do you remember this from last week? The flubber? We're going to do a little experiment with this again, but it takes a minute. So I'm going to put a GPS station on top of the flubber like this, and then I'm going to put this on top. And if you remember, the flubber will cause the other flubber to sink down. We're going to see how this GPS station moves. So let's set that aside for just a minute. So GPS stations are actually getting information from space. They're satellites circling the Earth, and those satellites help to tell the GPS station exactly where it's located in space, both horizontally and vertically. And so, hold on.
Stand by.
We're using new technology. It's very exciting. Here's my face. Did it turn off? I don't know what's happening, you guys. Hold on a second. No, I think it's fine.
Okay.
Okay. Are you ready? Thank you, by the way, for the new technology. Sorry for all of the difficulties. Anyway, so we have these two GPS stations down here, and we know that they're moving in different directions, say like this. What on earth could cause that? If we see that, we know there's something happening in between those GPS stations that's really important. So if we have these two GPS stations, what's actually happening is that the ground underneath of them is moving. The GPS stations are getting rafted along on top of the Earth. So let's watch these plates and see how they're moving. These would be like the tectonic plates, okay? So if that one's moving this way and this one's moving that way, we're going to move the papers to show that. See how they're moving relative to each other? This would be a strike-slip fault that we had talked about before, also called a transform boundary. And we can show, using arrows, the direction that those plates were moving. So this one was moving this way, and then this plate was moving this way. The San Andreas fault is actually a strike-slip fault, and so all of the GPS units nearby are moving apart from each other in the same way. Let's look at a different situation. All right, let's say that we have two plates that are like this. Instead of sliding past each other, this one doesn't want to stand up. These two GPS stations are moving apart like this. And that's showing that the plates that they're on are spreading. Now look at this one, it's moving much faster than this one, huh? So we would put a really small arrow on this one to show that it's moving slowly. And we'd put a big arrow on this one to show that it's moving more quickly. Now, let's see another example. Let's get another piece of paper. Put our GPS stations here, like this. What if they're moving towards each other? What happens if they're moving like this? That would be a convergent plate boundary. So that would mean this one is moving this way. This one is moving this way. So this kind of boundary creates thrust faults, where one block of rock gets pushed up and over top of another block. I didn't mention that when we have two that are separating, like the divergent boundary, that's what creates normal faults. And this is happening in the basin and range area of the United States. That's what creates the basins or the valleys, the mountains, which are the ranges. Okay, now let's quickly look at our little GPS unit that we put on top of the flubber. Because remember I said you can have these horizontal motions of the plate, but it can also show how the plates are moving up and down, or how the ground is moving up and down with time. In this case, this is like a glacier. This is the glacier, and then underneath of it would be like the lithosphere and the asthenosphere of the Earth. And remember, we set this on top. Look how it's tilted now. So it tilted over as the ground got pushed down. Now, what do you think will happen to this if we leave it? So it's tilted like this. As the ground comes back up, it will tilt again. If this was in the center, you would see it rising up as the earth underneath of it moves upward. And that's what we're still seeing in parts of Canada and the northern United States. There used to be an ice sheet there. Now all the GPS stations are showing an upward motion. How does this relate to volcanoes? We have a lot of GPS stations around active volcanoes. And that's because underneath volcanoes, there's a magma chamber, a place where the magma comes, and sometimes, unfortunately, it erupts out, right? Well, we want to know if that magma chamber is getting bigger. How could we do that? Well, we put GPS stations all around the volcano, but what would they show us if magma starts to come into the volcano? We can look at a balloon and watch. See all these little dots? These are like GPS stations. See how far away they are? What happens if I start to inflate the balloon in the way that a magma chamber would inflate beneath the ground?
Mom, why are you doing this?
See how all of the dots got farther away from each other? Now what happens if the magma were to drain out of the magma chamber? What happens to the GPS stations there? They both move down and closer together. It's the opposite of what happened when it inflated, where they moved up and farther apart. Isn't that cool? So, hold on please, Zach. This is what we predict that the plate motions would look like. Just like we drew, all of those arrows are showing the directions of the plate motion that we would expect, and the length of the arrow is showing how much the plate is moving, how fast it's moving. But this is what this is what we actually see. Lots of similarities, but also lots of differences. And those differences are really exciting because those are the places where we're really learning new things about how the ground is moving because of the GPS. So I'm going to put a lot of information on the Facebook page in the comments. If you have any questions, put those in there. For the teachers that are on here, this is also a really good way to talk about rigid body motion, looking at angular speed. You can use a fidget spinner like this, or you can use the example of a Ferris wheel. And in this case, the center of this, hold on please, sure, in just a second, this would be the pole of rotation. And then as you move outward, your speed would increase. So this is the same sort of thing that we use when we're looking at plate motion. And so I'll also include a link for how you can include these sorts of concepts and expand this idea of looking at plate motion and rigid body motion with your students. So thank you, happy Wednesday, and we'll see you next week. Gotta unlock my phone again. Okay, face.